Welcome! Today, we'll be exploring the problem number 1042, flower planting with no adjacent. This is a fascinating challenge that combines graph theory with creative problem solving. We'll walk through the problem, break it down step by step, and explore different approaches to arrive at the optimal solution. Let's dive in. In this problem, we are tasked with assigning flowers to a set of gardens while adhering to specific constraints. You are given n gardens, labeled from 1 to n, and a list of paths that connect some of these gardens. Each path signifies that two gardens are adjacent to each other. The goal is to plant exactly one type of flower in each garden such that no two adjacent gardens share the same flower type. Importantly, there are exactly 4 types of flowers available to choose from, and we need to find any valid flower assignment that satisfies these conditions. The input consists of an integer n, representing the number of gardens, and a list of paths, where each path is a pair of integers denoting a connection between two gardens. The output will be a list of integers, where each integer represents the flower type assigned to the corresponding garden, indexed from 1 to n. The output for the problem is a list of length n, where the ith element in the list corresponds to the flower type assigned to the i+1th garden. Let's go through an example to clarify this further. Suppose we have 3 gardens, with n equal to 3, and the paths are given as 1, 2, 2, 3, 3, 1. A valid output in this case is 1, 2, 3. Here's the reasoning: garden 1 is connected to gardens 2 and 3, so it can be planted with flower type 1 without violating the constraints. Next, garden 2 is connected to gardens 1 and 3. Since garden 1 is already planted with flower type 1, garden 2 can be assigned flower type 2. Finally, garden 3 is connected to gardens 1 and 2. Since garden 1 has flower type 1 and garden 2 has flower type 2, garden 3 can be planted with flower type 3. This ensures that no two adjacent gardens share the same flower type. Another example illustrates the scenario where n equals 4, and the paths are 1, 2, 3, 4. A valid output is 1, 2, 1, 2. Here, garden 1 is connected to garden 2, so it can be assigned flower type 1, and garden 2 can be assigned flower type 2. Garden 3 is connected to garden 4, but it is independent of gardens 1 and 2. This means garden 3 can be assigned flower type 1, and garden 4 can be assigned flower type 2. This assignment satisfies the conditions since no two adjacent gardens share the same flower type. Now, let's examine a slightly more complex example, where n equals 5, and the paths are given as 1, 2, 2, 3, 3, 4, 4, 5, 1, 5. In this case, garden 1 is connected to gardens 2 and 5, so garden 1 can be planted with flower type 1. Garden 2 is connected to gardens 1 and 3, so it can be planted with flower type 2. Garden 3 is connected to gardens 2 and 4, so it can be assigned flower type 3. Garden 4 is connected to gardens 3 and 5, so we assign it flower type 4. Finally, garden 5 is connected to gardens 1 and 4, so it can be assigned flower type 2. This assignment ensures that all constraints are satisfied. The problem also comes with some important constraints and edge cases to consider. The number of gardens, n, can go up to 10 to the power of 4, and the total number of paths can reach up to 2*10 to the power of 4. This means the algorithm must efficiently handle large inputs. Edge cases to consider include scenarios where there are no paths, allowing all gardens to be planted independently with any flower type, or sparse connections where most gardens can be assigned the same flower type. In contrast, dense connections or cycles require careful flower assignments to ensure no two adjacent gardens share the same flower type, even in the most complex configurations. To solve this problem, one initial approach we might consider is the brute force method. The idea here is straightforward: we try every possible combination of flower types for each garden and then verify if the constraints are satisfied. Specifically, for each garden, we assign one of the 4 flower types and then check all the paths to ensure that no two adjacent gardens have the same flower. However, this approach quickly becomes impractical. The time complexity grows exponentially, 4 to the power of n, because we have 4 choices for each garden and need to test all possible combinations. For a problem size as large as n equals 10,000, this is computationally infeasible. Additionally, it doesn't use the structure of the problem, such as the limited number of flower types or the sparse constraints imposed by the paths. This makes brute force a poor choice for this problem. A more efficient approach is the greedy coloring strategy. This method treats the problem as a graph coloring challenge, where each garden is a node and the paths or edges connecting those nodes. The goal is to assign a color, in this case, a flower type, to each node, ensuring that no two connected nodes share the same color. To implement this, we first construct the graph from the input paths. Then, for each garden, we assign the smallest flower type available that hasn't been used by its neighboring gardens. This process can be done in any order, such as going sequentially from Garden 1 to Garden North. An important observation here is that, since each garden can have at most 4 neighbors, there will always be at least one available flower type to assign. This makes the approach not only simple but also eliminates the need for more complex logic or backtracking. In terms of efficiency, this method runs in linear time relative to the number of gardens and paths, n plus e, as we process each node and edge once. It also has a linear space complexity, n plus e, to store the graph and results. The greedy coloring strategy stands out as the optimal choice for this problem due to several key reasons. First, it's highly efficient, running in linear time relative to the number of gardens and paths. This makes it well suited for large inputs, such as n equals 10,000. Second, it's conceptually simple. By always assigning the smallest valid flower type, we avoid unnecessary complexity. Third, the constraints of the problem guarantee that a solution will always exist without requiring backtracking. However, it's important to acknowledge the trade-offs. The greedy approach leverages the specific constraints of this problem: only 4 flower types and a sparse graph structure. In more general graph coloring problems with stricter constraints or more complex graphs, this approach might not work as effectively. Additionally, while the order of traversal doesn't affect the results here, it could in other scenarios, which is something to keep in mind. To summarize the final algorithm, we begin by building an adjacency list representation of the graph from the input paths. This step ensures efficient access to each garden's neighbors. Next, we initialize an array to store the flower type assigned to each garden. Then, for each garden, we examine its neighbors to determine which flower types are already in use. Based on this information, we assign the smallest available flower type to the garden. This ensures that the constraints are satisfied while maintaining efficiency. Finally, after processing all gardens, we return the array of flower assignments as the solution. This algorithm is designed to be both correct and efficient, leveraging the problem's constraints to minimize unnecessary computations and guarantee a valid result. To solve this problem, we need to assign one of 4 flower types to each garden in a way that no 2 adjacent gardens share the same type. The input consists of the number of gardens, represented by n, and a list of connections between them, given as pairs of gardens. Our goal is to return an array where each element represents the flower type assigned to a specific garden, ensuring that all adjacency constraints are satisfied. The first step in our approach is to represent the problem as a graph. We use an adjacency list structure to store the connections between gardens. For each garden, we maintain a list of its neighboring gardens. This representation allows us to easily traverse the graph and check the relationships between gardens, which is critical for meeting the constraints of the problem. The adjacency list is particularly useful here because it's space efficient and allows us to quickly access the neighbors of any garden. Once the graph is represented, the next step is to assign flower types to the gardens. We start by initializing an array called flowers, filled with zeros, to store the flower type for each garden. Then, for each garden, we determine the flower types that its neighbors are already using. This is done by collecting the flower assignments of all the neighbors into a set. From there, we choose the smallest flower type, from 1 to 4, that hasn't been used by any of the neighbors. This greedy approach ensures that the constraints are satisfied, as the problem guarantees that each garden can have at most 3 neighbors, leaving at least 1 flower type available for assignment. Once all gardens have been assigned a flower type, we return the flowers array as the result. The greedy approach works effectively here due to the problem's constraints. Since each garden has at most 3 neighbors, there is always at least 1 valid flower type available. Using an adjacency list not only simplifies the process of checking neighbors but also keeps the algorithm efficient in terms of both time and space. Additionally, the sequential assignment of flowers ensures that the constraints are respected at every step. This structure and approach allow us to handle the constraints without backtracking, making the solution both elegant and efficient. The time complexity of the algorithm includes the construction of the adjacency list, which takes O(e), where E is the number of edges, and the assignment of flowers, which takes O and *d, where d is the average degree of a garden, capped at 3. This results in an overall time complexity of O(n plus e). The space complexity is also O(n plus e), accounting for the adjacency list and the array to store flower assignments. Edge cases include scenarios like a single garden, which requires only one flower type, or gardens with no connections, which can be assigned any flower freely. Even in dense graphs where each garden has the maximum number of neighbors, the algorithm ensures a valid assignment due to the availability of 4 flower types. This greedy approach efficiently leverages the problem's constraints to guarantee a solution, making it both simple and robust. This code solves the flower planting with no adjacent problem by using a greedy algorithm to assign flower types to gardens. The goal is to ensure that no 2 adjacent gardens have the same flower type. First, the graph is represented using an adjacency list. This is achieved by using a default dict where each garden is a key, and its value is a list of adjacent gardens. The adjacency list is populated by iterating through the path's input. Next, an array garden_flowers of size n is initialized with zeros. This array will eventually store the flower type assigned to each garden, 1 based indexing. The algorithm then iterates through each garden, 1 to n. For each garden, it determines the flower types that are already used by its adjacent gardens. This is done using a set comprehension to collect flower types from the garden_flowers array for all neighbors of the current garden. After identifying the used flower types, the algorithm assigns the smallest available flower type, from 1 to 4, that is not in the used_flowers set. This ensures that the current garden does not share a flower type with any of its adjacent gardens. The result array garden_flowers is returned, which contains the flower type for each garden. The algorithm is efficient with a time complexity of O(n plus m), where n is the number of gardens, and m is the number of paths, making it suitable for the problem's constraints. Key edge cases are automatically handled. If there are no paths, each garden gets flower type 1. The graph's maximum size and complexity are handled efficiently using the adjacency list and set operations. Here, we start by importing the necessary utilities and defining our solution class. The method gardenOADJ takes 2 inputs, the number of gardens n and a 2D array paths that represents the connections between gardens. The first step is to create an adjacency list to represent the graph. We initialize a list of lists called graph, where each garden is represented as a node, and its neighbors are stored in the corresponding list. For each path in the input, we add the connections to both ends, ensuring the graph is undirected. Next, we declare an array called gardenflowers to hold the flower type assigned to each garden, initialized to 0 since no flowers are assigned yet. The main loop iterates over each garden. For the current garden, we create a Boolean array usedFlowers to track which flower types are already used by its adjacent gardens. By iterating through the neighbors of the current garden, we mark the corresponding flower types as used in the usedFlowers array. Now, we need to assign a flower type to the current garden. We do this by iterating through all possible flower types, from 1 to 4. For each flower, we check if it is not marked as used in the usedFlowers array. As soon as we find an available flower type, we assign it to the current garden and break out of the loop. This ensures that each garden gets the smallest valid flower type that is not already used by its neighbors. After processing all gardens, the gardenflowers array contains the flower assignments for each garden, satisfying the problem's conditions. Finally, the method returns this array as the result. This approach guarantees that no 2 adjacent gardens will have the same flower type, and the constraints are adhered to efficiently. To solve this problem, we start with a simple example where there are 3 gardens and 3 paths connecting them. The input specifies that Garden 1 is connected to Gardens 2 and 3, Garden 2 is connected to Gardens 1 and 3, and Garden 3 is connected to Gardens 1 and 2. First, we initialize the graph as an adjacency list to represent these connections. Using a default dict of lists, we map each garden to its neighbors. This gives us the graph structure. Garden 1 is adjacent to Gardens 2 and 3, Garden 2 is adjacent to Gardens 1 and 3, and Garden 3 is adjacent to Gardens 1 and 2. Next, we initialize an array, garden_flowers, to keep track of flower assignments for each garden. Initially, all values in the array are set to 0, indicating no flowers have been assigned yet. Now, for garden 1, we find that its adjacent gardens, 2 and 3, don't have any flowers assigned yet. This means we can assign flower type 1 to garden 1. At this stage, the garden_flowers array is updated to reflect this assignment, 1, 0, 0. For garden 2, we check its adjacent gardens, which are gardens 1 and 3. Garden 1 has already been assigned flower type 1, so we need to choose a different flower type for garden 2. The smallest available flower type is 2, so we assign flower type 2 to garden 2, updating the garden_flowers array to 1, 2, 0. Next, for garden 3, the adjacent gardens are gardens 1 and 2, which use flower types 1 and 2, respectively. The smallest unused flower type is 3, so we assign flower type 3 to garden 3. The garden_flowers array becomes 1, 2, 3, and all gardens now have flowers assigned. The final output for this example is 1, 2, 3. This demonstrates how we can assign flowers to gardens such that no two adjacent gardens share the same flower type. Now, let's look at a second example where the graph is disconnected. In this example, we have 4 gardens with 2 separate paths connecting them. Garden 1 is connected to garden 2, and garden 3 is connected to garden 4. We start by initializing the graph as an adjacency list. Gardens 1 and 2 form one connected component, while gardens 3 and 4 form another. The resulting graph representation is, garden 1 is adjacent to garden 2 is adjacent to garden 1, garden 3 is adjacent to garden 4, and garden 4 is adjacent to garden 3. Next, we initialize the garden_flowers array with zeros for all gardens, indicating that no flowers have been assigned yet. For garden 1, the only adjacent garden is garden 2, which doesn't have a flower assigned. We assign flower type 1 to garden 1, updating the garden_flowers array to 1, 0, 0, 0. Then, for garden 2, the only adjacent garden is garden 1, which uses flower type 1. To avoid conflicts, we assign flower type 2 to garden 2, updating the array to 1, 2, 0, 0. Next, we move to the second connected component. For garden 3, the only adjacent garden is garden 4, which doesn't have a flower assigned yet. We assign flower type 1 to garden 3, updating the garden_flowers array to 1, 2, 1, 0. For garden 4, the only adjacent garden is garden 3, which uses flower type 1. To ensure no two adjacent gardens share the same flower type, we assign flower type 2 to garden 4, updating the array to 1, 2, 1, 2. At this point, all gardens have been assigned flowers, and the final output for this example is 1, 2, 1, 2. This example highlights how the solution handles disconnected graphs by treating each connected component independently. Now, let's look at an example with a larger graph. In this larger example, we have 5 gardens with several paths. Garden 1 is connected to gardens 2, 3, and 4, and garden 4 is connected to garden 5. First, we represent the graph using an adjacency list. Garden 1 is adjacent to gardens 2, 3, and 4, garden 2 is adjacent to garden 1, garden 3 is adjacent to garden 1, garden 4 is adjacent to gardens 1 and 5, and garden 5 is adjacent to garden 4. Next, we initialize the garden_flowers array with zeros for all gardens. For garden 1, the adjacent gardens are gardens 2, 3, and 4, none of which have flowers assigned yet. We assign flower type 1 to garden 1, updating the garden_flowers array to 1, 0, 0, 0, 0. For garden 2, the only adjacent garden is garden 1, which uses flower type 1. We assign flower type 2 to garden 2, updating the array to 1, 2, 0, 0, 0. For garden 3, the only adjacent garden is garden 1, which uses flower type 1. We assign flower type 2 to garden 3, resulting in 1, 2, 2, 0, 0. For garden 4, the adjacent gardens are gardens 1 and 5. Garden 1 uses flower type 1, so we assign flower type 2 to garden 4, updating the array to 1, 2, 2, 2, 0. Finally, for garden 5, the only adjacent garden is garden 4, which uses flower type 2. To avoid conflicts, we assign flower type 1 to garden 5, updating the garden_flowers array to 1, 2, 2, 2, 1. With all gardens now assigned flowers, the final output for this example is 1, 2, 2, 2, 1. This demonstrates how the algorithm efficiently assigns flowers to gardens even in larger graphs, ensuring that no two adjacent gardens share the same flower type. By iteratively processing each garden and considering its neighbors, we can always find a valid assignment that satisfies the problem's constraints. To analyze the time complexity of this solution, let's begin by considering the process of building the adjacency list. For each path in the input, we add the connected gardens to each other's adjacency lists. Since there are m paths and each addition operation is O(1), the total time for this step is O(m). Next, as we iterate through the n gardens, we determine which flowers are already used by accessing the garden's neighbors. The number of neighbors across all gardens is bounded by 2m because each edge appears twice in the adjacency list. Accessing the flower type for a neighbor is O(1), so the total time spent across all gardens to determine used flowers is O(m). Finally, assigning the first available flower involves iterating through 4 flower types, which is a constant operation for each garden. Therefore, flower assignment per garden is O(1). When we sum up the time spent iterating through all gardens, we get O(n) for the gardens themselves plus O(m) for the neighbors, yielding O(n plus m). Now, let's look at the final step, constructing and returning the result. The result is stored in the garden_flowers list, which is built in O(n) time since it simply involves copying the flower assignments for all gardens. Combining all these steps, the total time complexity becomes O(m) for the adjacency list, O(n plus m) for iterating through the gardens, and O(n) for the result. This simplifies to O(n plus m) overall. This efficiency is well suited for sparse graphs, where the number of edges m is typically proportional to n. In such cases, the algorithm runs in linear time relative to the size of the graph, making it scalable even for large inputs. Let's analyze the space complexity of this solution. First, we store the graph as an adjacency list, where each garden has a list of its neighbors. Since each edge is stored twice, the space required for this is O(m). Next, we use the garden_flowers array to store the flower assignments for all n gardens, which requires O(n) space. Additionally, during the iteration over gardens, we use a temporary set, used_flowers, to track the flower types assigned to adjacent gardens. Since there are only 4 possible flower types, the size of this set is constant, contributing O(1) space. When we add these components together, the total space complexity is O(m) for the adjacency list, O(n) for the result array, and O(1) for temporary storage, leading to O(n plus m) overall. The space complexity of O(n plus m) is efficient for this problem, especially given the graph sparsity in most practical scenarios. When comparing this optimized approach to a naive solution, the difference is striking. A brute force approach would require checking all possible combinations of flower assignments, which has a time complexity of O(4 to the power of n), as each of the n gardens could potentially take one of 4 flower types. This is clearly infeasible for larger values of n. In contrast, our optimized approach leverages the sparsity of the graph and uses a greedy algorithm to achieve a time complexity of O(n plus m) and a space complexity of O(n plus m). This efficiency ensures that the solution remains practical even for large inputs, making it both faster and more memory efficient than the naive approach. Finally, let's evaluate the best, average, and worst-case scenarios for this solution. In the best case, the graph is very sparse, such as a tree structure with m equal to n1. Here, the time complexity remains O(n plus m), but the constant factors are minimized due to fewer neighbors per garden. In the worst case, the graph is dense, meaning each garden is connected to many others. However, since the number of edges in an undirected graph is capped at O(n squared, the time complexity still holds at O(n plus m). For the average case, which is typical in practice, the graph remains sparse with m proportional to n, so the time complexity is O(n). The correctness of the algorithm is guaranteed by the greedy approach, which assigns a valid flower type and constant time per garden. With only 4 flower types in sequential graph processing, the algorithm achieves optimal performance within the input constraints. When solving the flower planting with no adjacent problem, there are several common mistakes to watch out for. First, one of the biggest issues is not handling constraints properly. This happens when adjacent gardens are assigned flower types without ensuring they are different, often because constraints are only checked after the assignment. The best approach is to use a constraint checking mechanism during the flower assignment process to ensure that each step maintains validity incrementally. Another mistake is overcomplicating the solution. Many candidates use advanced techniques like backtracking or recursive DFS, even though a simpler greedy or iterative approach is usually sufficient. Always analyze the problem requirements to determine the simplest correct solution. Additionally, inefficient brute force implementations can be a trap. Iterating through all possible combinations of flower assignments leads to exponential time complexity, which is impractical for larger inputs. Instead, optimize by leveraging adjacency information to dynamically limit choices. Finally, errors in the graph representation, such as forgetting to handle bidirectional edges, can lead to incorrect constraints. To avoid this, use a proper adjacency list or matrix to accurately represent the graph and ensure all edges are accounted for. Edge cases are another important consideration. Disconnected gardens, scenarios with no constraints, or the smallest input size like n equals 1 are often overlooked. To avoid pitfalls, test your solution thoroughly with both minimal and maximal edge cases. In interviews, it's also important to understand the underlying graph structure of the problem. The gardens and constraints form an undirected graph, and using an adjacency list representation can simplify your work significantly. Greedy approaches typically work well here, as you can assign flower types incrementally while ensuring constraints are satisfied. Additionally, when the number of flower types or gardens is small, fixed-size data structures can be used to optimize performance by eliminating unnecessary computations. Finally, interviewers often appreciate clear explanations of trade-offs. When discussing brute force versus optimized approaches, emphasize why one method might be computationally impractical while another is more efficient. This demonstrates not only your problem-solving abilities but also your understanding of time and space complexity. This problem is closely related to several other graph-based problems, such as LeetCode 886, possible bipartition, LeetCode 785, is graph bipartite, and LeetCode 133, clone graph. These problems also involve reasoning about constraints in graph structures, making them great practice for building intuition. When it comes to alternative approaches, the preferred method here is greedy assignment with adjacency checks. This approach is simple, efficient, and runs in O, n plus e, where n is the number of gardens and e is the number of constraints or edges. Backtracking is another option, but it's computationally expensive, running in O, 4 to the power of n. This method should only be considered when the input size is very small. Finally, graph coloring techniques using DFS or BFS can be applied, especially for more complex variations involving additional constraints, like minimizing the number of flower types. However, for simpler cases like this one, graph coloring is often overkill. Choosing the right approach depends on the specific problem requirements and constraints you're working with. Great job! We've successfully tackled the problem flower planting with no adjacent. We reviewed the key concepts of graph coloring and optimized our solution for efficiency. Don't stop here, keep practicing similar problems to strengthen your understanding. Thanks for watching, and I'll see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!